Hello everyone, we are Orion SCUA, and in this opportunity we will be reporting the progress of the team for the competition organized by Latin American Space Challenge.
The Orion rocket mission is going to reach the 3,000 meters above the ground. To achieve this, the mission is going to have three important moments. The direct parachute deployment is going to be near to the zero velocity point. If the signal fails, it will be an emergency signal from the ground station. The next important moment is at 500 meters above the ground. At this time, the main parachute will be deployed. 10 meters after, the transat, our payload, will be ejected and it will be glide until reach the ground level.
The first step for designing a solid rocket motor is to go through the state of art of solid rocket motor construction, design, propellant, characteristics, and so on. Our most important guide for the motor development were some NASA technical reports that are public nowadays. The methodology we used was something similar to the sequence used on the book Solid Propellant Crane Design. The last contest requirements were reviewed. Then three main independent fields were developed: the propellant characteristics and selection, in our case KNSB, the ballistic parameters were obtained running a flight simulation preliminary code, getting the necessary thrust curve for the estimate weight, and the envelope constraints. Using the independent data, propulsion equations, nozzle relations, and mechanical design, we get the motor geometry. Then a validation is running using the software OpenMotor. Finally, the motor characteristics are exported from OpenMotor and imported to OpenRocket in order to perform a more complex flight simulation. The motor has an outside diameter of 95 millimeters, is a L1915 KNSB motor, and is able to impulse 13 kilograms to 3 kilometers.
Talking about the avionics subsystem, the general block diagram can be seen on the screen, which is composed of 6 different and important stages, like for example, power stage, recovery, control stage, and management and processing. The avionics will be based and developed by members of the group and implement sensors, actuators, and different devices for this purpose. Some of them are barometric pressure sensor, IMU, and GPS. Actually, there is a PCB based on modules that later will be unified. On the other hand, there will be a communications and telemetry system. Its operation will be based on LoRa modules at 433 MHz as operation frequency. Additionally, the graphic interface and data processing system is currently in process. Finally, a correct apogee detection is crucial for the success of the mission. In that sense, we have 3 different options for the redundant electronics, which can be seen on the screen. At this moment, the team is selecting the best option in terms of delivery, availability, and efficiency.
The frame structure is designed to be modular, so it has 3 parts, which are the noise tone or ogive, the body frame, and the motor frame. The avionics, expulsion systems, and the transat, as our payload, are going to be attached to the body frame rack. The rack is a circular structure designed to ease the rocket assembly. The motor frame is going to be responsible for the alignment and support of the rotor motor and fins. For the first aim, we will use support rings. One of them, the principal one, is going to be used as a joint part for the principal body and motor frames. Finally, the noise cone is going to be attached to the principal body frame using nylon fasteners, which will be broken by the expulsion system using a force of 250 newtons. This would be a critical point of the design of the expulsion system. All the design is themed for additive manufacturing, using metal reinforcement in the critical structural parts of the frame. In that way, we can reduce weight and material cost of the rocket.